Okay. So first, I'd like to thank Alex and Johannes for inviting me. So first, let me give a very short introduction to the cluster algebra. So to define a cluster algebra, the most important data is a quiver. So a quiver, we ask quiver to have those quiver without loop and 2 cycles. But I need to clarify that this is not the general setup, but it's enough for the purpose of this talk. So what we do is we'll first attach to each vertex of the quiver a variable. So viewing as an element in the field of rational functions. Then we can mutate at each vertex of the quiver. So that means we are going to change the quiver into a new quiver, and the vertex, the variable attached to the vertex to a new variable. So the procedure is the following. So for each pair of arrows like this, we introduce a new arrow. And then we reverse the arrows here. So remember that we first fix the vertex u. So this operation is really local. So in the sense that you don't really need to know the vertex arrows which is not adjacent to u. So once you finish the step 1 and 2, you might get some 2 cycles. Then you need to delete those 2 cycles one by one until there's none left. So that's the mutation rule for the quiver. Well, then the variable will change as well. So it will obey the following rule. So for all the arrows coming in U, you get this product. And all the arrows coming out of U, you get this product. Then take sums, then divide by the original one. So this is our new variable. So the initial one here, look at the set, original generator is called an initial cluster. So after mutation, the XU is replaced by the new variable. So this is the new cluster. And this procedure can be applied recursively. So in this way, we get many different clusters. And for those of you more familiar with this cluster varieties, so this is essentially the same. So viewing this as a birational morphism. So this is a rule to gluing the torus in the cluster A variety. So this is equivalent. Now the cluster algebra is the subalgebra in this field of rational functions generated by all possible cluster variables. And the upper cluster algebra will contain all the elements in here, which is universally Laurent. So universal here means it is a Laurent polynomial if expanded in any cluster. So this is same as the ring of the regular functions on the cluster A variety. There is also mutation rule for the so-called Y seeds. And that is the rule to describe how to glue in tori in the cluster X variety. So cluster X variety, in fact, is not always separated, but it's still interesting in some way because from the point of view of mirror symmetry and other perspective. And more generally, if we start with a matrix which with a skew symmetrizable principal part, will give rise to a pair of cluster variety, A variety and X variety, and their long-length dual denoted by A and X check. There is a conjecture stated by Fock-Goncharov. So first, it's good to observe that this gluing morphism is actually a positive morphism. So the variety we get can be tropicalized. The Fock-Goncharov duality conjecture says that the tropical points of X variety will parameterize the basis of a ring of regular function on the X variety. And we can reverse the rule of A and X. And now we know that the duality conjecture fails in general. But with, sorry, someone's raising hand.
Someone just joined the meeting.
Ah, I see. But it fails in general, but can still hold with some very mild assumption. And or we can replace it with a formal version. So there is a formal version of this duality conjecture. So this is the one of the results of GHKK paper. So our approach is from this additive categorification. So let me briefly remind you, what do I mean by this categorification? So roughly speaking, that says there exists some cluster character denoted by CC. We're sending a class of objects in certain additive category, so onto a set of cluster variables. So additive simply means the category is additive, and that gives you additional requirement that the character would respect this addition here. So the direct sum will map to the product in the cluster algebra. There are two well-known approaches to this. There are two well-known additive categorification. So one is given by the quiver with potential. This is a result of Dixon, Wayman, Zalevinsky. Then the second approach is through the generalized cluster category. So today I'll mainly follow the first one, but one or two is more or less equivalent. So what is a quiver with potential? A potential on a quiver is a linear combination of oriented cycles. Now, so start from a potential. So usually we can choose a potential. Then from the potential, we can have a Jacobian, so-called Jacobian idea. So how to form the Jacobian ideas? For each arrow, there we can define a non-commutative partial derivative. So later I will give you a very concrete example. And for each partial derivative can be applied to the potential and get an element in the path algebra. So in fact, we need to look at completed path algebra. Then the Jacobian algebra is the quotient of the path algebra by the Jacobian ideal. A very important result of this quiver of the theory of quiver potential is that the quiver mutation we just introduced can be linked to the mutation of quiver with potential. But since today's talk, we don't really explicitly use mutation, so I'm not going to record this. So here's an example. Let's look at this 4-vertex quiver. You have two oriented cycles like this, two. Then we set potential like this. This is one cycle subtracted by the other one. Then we apply the partial derivative, since this is a non-commutative algebra. So somehow we still have the derivative actions works really like the commutative case. So as you can see here, if you take derivative with respect to A, we get CB, just like take here, and the rest is vanished. And somehow special case, the special situation is if you take this partial derivative with respect to the arrow C, you will get a two-term. So anyway, so start with a potential, you would get an ideal. So you get an algebra with relation. So in particular, we would have a representation theory of this algebra with relation. But the first step is actually not to look at the representation. We are looking at the category of presentation. So let me just give a very short introduction on this presentation, the category of presentation. So here presentation, I mean a morphism between two projective representation. So one will be denoted by P minus, and the other one will be denoted by P plus. So this is a morphism. So this is a presentation. The additive category of all presentations is Knut-Schmidt. and the corresponding homotopy category can be triangulated. And then I define what is the weight of a presentation space. So weight, this weight is a vector. This is a vector indexed by the number of vertices by the vertices of the quiver. But here the notation I think is a little bit heavy, so it's better to look at this one by one. So recall for the algebra with relation, the indecomposable projective representation corresponds to each one-to-one correspondence to each vertex. So Pi here is the indecomposable projective representation. And here beta I is a vector. So beta is a vector. So beta I times Pi simply means the Pi have multiplicity beta I in this direct sum. And here, this is a vector notation for choose maximal. And so simply says the thing in brackets simply give the multiplicity of the each indecomposable in these projectives. And here the home is just all those morphisms from this projective to another projective. So this is the presentation space. And now we define a vector space called E. So E of two presentations by definition. So one presentation home with the other one, but with some shift. So here I view a presentation as a complex. So the first one, P minus, is in fixed degree, say -1, and P plus is in degree 1. Sorry, it's in degree 0. So in this way, I'm talking about shifting these two complex and take a home. And once we have a presentation, we can home with a representation. And for this one, I denote kernel by this home dm and co-kernel by edm. And for this one, I think very easy to see that this is nothing but home of a representation of the co-kernel of D with the representation M. Yeah. So later we will always do the following. We will take a co-kernel of the presentation, and the co-kernel is in fact a representation. So here is an observation. Sorry, it's a result of Fomin and Zalevinsky. They proved that for any cluster variable can be written as follows. So x to the degree g. So here I used this vector notation. And here times a polynomial fy. And y is a monomial in x. In fact, there's an explicit formula for y, but let us ignore this. So the point is of Dukes, Wayman, Zalevinsky is that those G vector can be viewed as elements in the K group of the presentation K group of the category of presentation of Jacobian algebra. So the question is, so the cluster will correspond to what kind of G vectors? So recall that cluster will have n different variables. So each one would have a G vector correspond to them. But here is a technical condition. But most important is this condition. So this is really the characteristic condition for a set of G vector form a cluster is the following. So the E of minus GI and minus GJ should vanish. So recall we defined the E of two presentation. But here, so here I put a vector here. So you can guess what does it mean. So I take a presentation space of weight negative GI, then pick a generic presentation there. And the same for the here. I pick a generic presentation in that presentation space. Then I take the generic value of the E should vanish. So you may wonder what's the representation theoretical meaning for the vanishing of those E's. So here's the answer. So we call a weight vector delta. So here I use G, but here I use delta. That's the all denote a weight vector. But difference is usually usually you can think the delta vector is the negative the G vector. So they differ by a negative sign. So a weight vector delta is called indecomposable if the general representation in the presentation space is an indecomposable object. And we also call that if we write a delta vector as a direct sum like this, and this is called the canonical decomposition of the delta. If the general elements in the presentation space of weight delta will decomposes into indecomposable ones, each of weight delta I, then this is called canonical decomposition. So a result proved more than 10 years ago is that this is a canonical decomposition if and only if there are virtual E invariants. This E, sorry, it's just the dimension of the big E is vanish for I is not equal to J. This is the representation theoretic meaning for vanishing of this EI J. So now we somehow finish the explanation for the first part. Then now we focus on the second piece, the Fy. So Fy is related to F-polynomial of a representation. So let me first define what is the F-polynomial of a representation. So here representation is a representation of a certain quiver with relation. I take a representation M, then this GREM means the variety parametrizing or this quotient representation of dimension E. So this is a projective variety. Then we take the topological Euler characteristic and take the generating function. This is the F-polynomial. So easy to see that for each G vector, there's an open set in the presentation space, such that if I take the co-kernel, then take the quiver Grassmannian, the Euler characteristic will have the constant value on this if you vary the representation on the if you vary this co-kernel on this presentation space, you get a constant value on this open set. And the generic character is the following formula. I map G to xg times, you take a co-kernel, get a representation, then take the F-polynomial. And it is known that this generic character will map the G vector to an element in the upper cluster algebra. So this is first introduced by Dupont, then further studied by Plamondon. And in many cases, they prove to form a basis of the upper cluster algebra. So now you can guess this G is like a parametrizing, it's like a tropical points. They parametrize the ring of regular functions. And for the E-rigid G vectors, so in other words, this generic characters will give the cluster variables. So I'm not state those things in a historical order because actually the Caderouche-Chaperton first formulate first give this kind of formula, but for a very small class of quiver. But later Dixon, Wieman, Salevinsky, they generalized to a very large class of quiver with potential. And I want to point out that this Euler characteristic is not always positive. They're only positive for cluster variables. In general, they can be negative. So what I want to do is I want to tropicalize this F-polynomial, even if the coefficient here can be negative. So somehow I want to make, I need to define kind of a tropicalization. So I want to do it in a slightly general framework. I'm not just for Jacobian algebra. I'm going to do working with for any finite dimensional algebra presented as quiver with relation. So consider any finite dimensional representation of this algebra. So the tropical F-polynomial of M is the following function. So I'm going to view the weight vector as elements in the dual space. So Q0 here is the number of vertices. Sorry, it's the vertex set of the quiver. So this is a weight vector I view as a one in the dual space. It's going to pair with in using the usual inner product with this dimension vector. So what I'm doing is pick all possible sub-representation of M, take the dimension vector, then take the pairing, then take the maximum. So this is my definition for the tropical F-polynomial. So if you look at the definition of F-polynomial, it's easy to see if F-polynomial have non-negative coefficients, then this tropical F-polynomial is just the usual tropicalization of this Fm. Yeah, I think even this one can have negative coefficients. This defined tropical F-polynomial still have representation-theoretical meaning. So here I'm going to introduce the main result. So first, let me define two homological invariants, Hom delta M. We just defined Hom dm. D is a presentation. So as you can guess, if you replace a presentation by its weight vector, that simply means I take a generic presentation in this presentation space and do the same thing, take a kernel and co-kernel. And dimension of the kernel will be this guy, and dimension of the co-kernel will be this guy. So the result says that if you evaluate the tropical F-polynomial at the weight vector, and then you get this Hom. On the other hand, there is also a notion of a dual F-polynomial. So before I used this sub-representation to define the tropical F-polynomial. So if I use quotient representation, that is the dual F-polynomial. So that one will give you the other one. But the theorem is not so nice because the n here, the statement there's n, right? And there's no way to determine this n very easily, I think. But in some cases, one would expect this equation will hold for all n. So for example, if we have this condition equal to 0, so a special kind of set of delta vector, so then the n can be taken for any natural number. But if we focus on some special class of algebra, say the Jacobian algebra, the theorem can be greatly improved. I think I will do it later, but just keep this keep this formula in mind. And one immediate implication of this result is that we can give a presentation for the Newton polytope of a representation. So it's easy to see that the tropical F-polynomial is completely determined by the Newton polytope of a representation. So the definition is obvious. I take all possible sub-representation and take the dimension vector, then take the convex hull. That's the Newton polytope of a representation. So now the presentation of the Newton polytope is given by the following formula. And as you can see that the delta vector here works like a normal vector. And here is like the shift, this homological, the invariance give you the shift of the hyperplane. So this is the hyperplane presentation for the Newton polytope. And then if we focus on the case of quiver with potential, the previous theorem can be a little bit improved. Here's the situation. So basically, we can make this n equal to 1. But the price is also paid because we need the algebra to be quiver with potential, and the representation M is not any representation. It should be negative reachable. It's a technical condition that simply says this is kind of a mutation representation can be obtained from mutation. And as a corollary, so for any delta vector, you can compute the dimension of the generic co-kernel. So you just need to understand, or you can just compute all the tropical F-polynomial for this injective representation. then you evaluate on this delta vector. Then you get the dimension vector of at the position I. So this is a very, I think even this simple corollary is not known previously. And if you look at this formula, there's two arguments, delta and m, which are not completely symmetric, because of course here this simply means you take a co-kernel. This should be viewed as a representation. But here m is there's additional requirement on m, which is negative reachable. In general, I have the following conjecture. So if we do make this m another vector g check, then we have this, because this is just motivated by these two equations. I should conjecture that they should be same. And this conjecture actually has some important implication, which I will explain later. Maybe I need to explain a little bit because here the delta check is also a weight vector, but here to define this home m and the weight vector put in the second argument simply means I'm going to working with injective presentation rather than projective presentation. So, but the theorem goes very similarly. So, so we will come back to this conjecture later. Another important application is that so if you look at this one, so assuming that somehow in the formula the rule of delta and m is symmetric, or they are in an equivalent rule, then this will give a way to really compute the generic Newton polytope. That means if this m is a generic kernel or co-kernel of some presentation, then I can compute the Newton polytope. So in fact, it's easy to see to compute such Newton polytope is to examine because if you really want to use the theorem, there's a condition here, m is negative reachable. So this simply says that when if you want this algorithm to work, if you look at some vertex of the Newton polytope, then take this normal cone, and sufficient condition it will be that in the normal cone should contain certain cluster. Well, I cannot prove this one in general, but this turned out to be true for Quiver without any cycle. So put zero potential. That shows that each normal cone of any generic Newton polytope will contain a cluster. And then I can use the method here and the theorem here to have an algorithm to explicitly compute the Newton polytope. Well, I'm not going to, because maybe the time, I'm not going to give you the detail for the algorithm. Maybe we can come back to the algorithm later. So here I explain another motivation why we care about the Newton polytope. There's a remarkable universally positive basis consisting of theta function for all cluster algebra introduced by Grosshackening, Q, and Kontsevich. Then for any delta vector, there is a theta function, which is in this form. And here you see this is like x to the g vector. And this part looks like F-polynomial. But certainly they are different from the usual F-polynomial in general. Well, another very interesting positive, actually quantum basis, is called triangular basis, was introduced by Qin as a far-reaching generalization of Berenstain-Zalevinsky's triangular basis. Well, it have the similar form. So x to the power of some delta vector times something like a F-polynomial. Yeah, I need to point out that in general, the theta basis need not to be a polynomial. This part can be a series. But for the time being, let's assume this is a polynomial. And they are all universal positive, so they can be tropicalized. Now, yeah, so can we determine the Newton polytope of these guys? But in fact, I have a conjecture. The Newton polytope of the theta basis, this part, the Newton polytope of this part and this part, they are same as the generic Newton polytope we just introduced. And moreover, the coefficient for the F-polynomial for this part, I mean, I'm not consider all the coefficients. I only consider those coefficients corresponds to the vertex in the Newton polytope. The conjecture is that those coefficients should be all ones. Yeah, so maybe the last application is about the Fock-Goncharov duality pairing conjecture. So in the beginning, I stated the duality conjecture. Here is a duality pairing. So what is this? So this is extended part of the duality conjecture. So recall the duality picture simply says the tropical points are mirror parameterized basis of the ring of the regular function. So here, so for example, if I take a tropical point in the A variety, then we know it parameterizes then it parameterizes a basis. So I map to a basis in the function on the X variety. After tropicalization, I get a tropical function. Then it can evaluate at the tropical points of the X variety. So like I get this kind of pairing. And we can reverse the rule of A and X. So in priori, the two kind of different pairing will give you different result. The conjecture says that these two pairings are actually equal. So we are going to prove this actually equal in some special cases, not all cases. So the way to prove it is, as you can guess, is to using the representation-theoretical machinery. So for that pairing, both are equal to this. As you can guess, the home should appear. This is like a certain tropical F-polynomial evaluates certain vector, but with certain shift. And there's another shifted factor here. Yeah, actually, the equality is not so trivial, even from the representation theoretical point of view. So one is actually compute home is from the injective resolution. The other one actually compute this home from this from the injective resolution of this one. The other one from the projective resolution of this one. So so this is not completely trivial. And what is the two situation that we proved? So one situation is if the quiver is mutation equivalent to an acyclic quiver. The other situation is that if these two guys, so actually we only require one of them is corresponds to a cluster variable. And let's come back to the previous conjecture. So if saying that if we have this equality of this kind of pairing, if this is true, then this kind of pairing also works. I mean, they should equal in all skew symmetric case. Moreover, if we know that B is invertible, this one can be written in a more symmetric and beautiful form like this. But in general, B certainly is not necessarily invertible. So this is our interpretation of Fock-Goncharov duality pairing. Okay, so we have some further interesting result concerning the Newton polytope and the coefficient. So first result is I take a representation of M. We'll look at a vertex on this Newton polytope. It turns out that the corresponding subrepresentation, the Grassmannians, is just a single point. So there is a unique subrepresentation correspond to each vertex. And actually, conversely, it's not completely true. We need some additional requirements. For example, we need to, if we require the representation is generic, then it is true conversely. And this result in particular shows that the Newton polytope of a representation is same as the usual Newton polytope of the F-polynomial. Yeah. Here is a conjecture, more or less motivated by this theorem. So let's consider the F-polynomial of a cluster variable. Then we take the Newton polytope of this F-polynomial, look at the vertex. The claim is the coefficient on the vertex is always 1. Yeah, actually, I proved that conjecture holds for all acyclic cluster algebra. But conjecture says it holds for any cluster algebra. But only states for cluster variable. It is not true for any basis or any particular basis. But for cluster variable, it is true. The second one is I consider the restriction, the very naive things. If you can do is you restrict a polynomial on particular faces or facet. So you just look at the particular you look at the degree on the particular faces. Then you sum up. You just take a combination of all those coefficients on the. I mean, you just restrict each monomial term on these faces. So that's what I mean by restriction polynomial on a particular faces. So this restriction also have a representation-theoretic interpretation. So suppose the delta is a normal vector of the Newton polytope. Then the restriction of this Fm to this facet is given by the following formula. The formula have several ingredients. For first one, the pi delta is a functor. It will map the representation M to a different representation of a smaller quiver, different quiver. And the smaller quiver can be produced by an algorithm. Usually it's not in a naive way. It's not just delete a vertex or delete an arrow. So it's not a simple procedure. But anyway, you get another F-polynomial of another representation. And here the iota delta is a very simple change of monomial, change of variable. So this is kind of trivial thing. But we have additional factor, y to some power, and power is given by this functor. This is called this a certain stabilization functor, which I don't have time to give the detail. So you somehow you have a representation. The functor will naturally produce an delta stable representation, and then it will take a dimension vector. Yeah, so there's another point of view. You view those delta as a stability condition. You get the power here, and the result can be generalized to arbitrary phases, not necessary of dimension 1, codimension 1. And the third property is about saturation. So we call a polynomial is saturated if for any lattice point in the Newton polytope of F, the coefficient is not vanishing. So that in that case, I call the polynomial is saturated. So the conjecture is the support of a polynomial of any cluster monomial. So by cluster monomial, I mean the product of cluster variables in a fixed cluster in a fixed cluster. So any cluster monomial is saturated. I mean F-polynomial of a cluster monomial. And I proved that the conjecture actually holds for acyclic cluster algebra. So let me talk about some other aspect of the combinatorial of the Newton polytope. So first, let's think about the duals. So we previously we saw the normal cone is also interesting. So one interesting question is whether a normal cone contains a cluster always. Here the situation is I give you a finite many cluster, say delta 1 up to delta n. So each cluster will be a set of delta vectors, satisfy certain condition, right? Then I can always construct a representation such that those deltas, each one will spans the normal cone of the Newton polytope. Yeah. So why we care about this? So there's some sort of a more global construction. So for those representation of for Newton polytope, I can put all the normal cone together and get a completed. I can make it a fan. So fan. But in general, we can define for algebra the so-called cluster fan. So that is constructed from the clusters by put all cluster together, we get a cluster fan. Yeah. When the algebra is Jacobian algebra, this is the usual cluster fan of a cluster algebra. So now I'm going to define a generalized version of the cluster fan. So recall for cluster, the defining condition is like this, right? But there's some technical condition like we ask those delta to be negative reachable. But for the generalized cluster fan, I don't require those deltas are negative reachable. So this is the only condition. So it turns out that those generalized cluster fan is certain refinement of this fan of the representation. I mean, the fan of the Newton polytope. Then let's look at the one skeleton of the Newton polytope. So recall that for each vertex, there is a unique sub or quotient representation corresponds to that vertex. So now I pick an edge. So for each 2 point, these the endpoint of this edge, we have a unique representation. So I proved that, in fact, these two representations must have the containment relation. So either one contains the other, or the other hand. And I also have this representation-theoretic interpretation for these two representations. We can use the functor to construct this L minus and L plus. Now assume that if L plus contains L minus, then we take the quotient. It turns out that this quotient is a direct sum of isomorphic real Schur representation. So real Schur representation is special class of representation. So by definition, a representation is called real Schur if the surf home is equal to the base field, and the first extension of these two or the surf first extension of the representation is vanished, but there is no other requirement for higher extension, surf higher extension. Yeah, so the quotient is always a direct sum of single real Schur representation. So since we have this kind of always have the containment, so we can put additional ordering on the vertices. So if one contains another, we give orientation to the edge. So in this way, we obtain a quiver on the one skeleton. So this is what I call the edge quiver. So later I'm going to show you, I will show you a picture for those edge quiver. Okay, finally, I have some application for some special class of algebra. So an algebra is called cluster-finite if this algebra have only finite many cluster. So you have only finite meaning, those G vectors or delta vector, they form a cluster, but there are only finite many of them. Then we take all E-rigid representation, take direct sum. Then I take the Newton polytope of this direct sum. Then the claim is the normal fan of the Newton polytope is the usual cluster fan of the algebra. I think even when the algebra is the Jacobian algebra is already very interesting because this one will be the cluster fan of the corresponding cluster. And in this case, the edge quiver will be the exchange quiver of the algebra. So in case of Jacobian algebra, this will be the exchange graph of the corresponding cluster algebra. So this proposition tells us that heuristically we can view the normal fan of infinite. So recall we defined the generalized cluster fan. So this generalized cluster fan can be viewed as a normal fan of infinite dimensional representation. So somehow we take all representations and take then make a direct sum of them, and you get an infinite dimensional representation. Of course, that doesn't really make sense if you take this kind of Newton polytope. And the second class of algebra is the preprojective algebra of the Dynkin type. So in this case, I'm not going to take the direct sum of all representation. I only need to take the direct sum of projectives. Yeah, but if you like, you can take all. So if you take the direct sum of projective, then if I look at the Newton polytope, the vertices of the Newton polytope will be labeled by the ideal of the preprojective algebra. And in fact, we know that ideal is labeled by the corresponding wire group of certain Dynkin type. And the fan, if I take the fan of this Newton polytope, I will just get the cluster fan of the representation of the preprojective algebra. In that particular case, it is a wire, so-called wire fan. Okay, so in the end, I show you an example. So for this quiver with relation, as you can see, the quiver is like this, and the relation is the vanishing of AB. Sorry, I should put maybe BA here. And so this is not a Jacobian algebra. And easy to work out that there are 9 indecomposable representations for this quiver. So except for those projective, injective, simple representations, there are another 2 which is slightly complicated, but easy to describe as a co-kernel of a generic presentation. And so it turns out the cluster fan of A, to get the cluster fan of A, what we do is I take the direct sum of all these representations. But but in this case, we actually don't need to take all of them. We just so one possible choice is I take some of them. But I mean, what you can do is actually you can take it one by one and take the Minkowski sum. You can take the Newton polytope one by one and take the Minkowski sum of them. That will be the Newton polytope of the direct sum of them. So what you get is the following picture. As you can see that there are 18 vertices. So each vertex will correspond to a cluster. And so for that algebra, you'd have 18 clusters in total, which each correspond to a vertex. the normal cone is in fact this cluster. And the arrow will give you this order as defined before. And here, the representation appear here is the quotient. The bigger one quotient multiplies the small one. I always get some multiple of a real sure representation. Yeah. So this is the picture. Okay, I think that's all for my talk. But if you're interested in, I can still give you, because there's still a few minutes left, I can give you some description of the algorithm for computing the Newton polytope. Just so to compute the Newton polytope, so I only need to work out this kind of thing. The number, I need to work out the number home of this one. And I can compute the home in two different ways. So one way using this, the other one is using this. It turns out that one way is easier because if M is reachable, this Fm, the tropical F-polynomial, can be computed using the mutation algorithm. So here's how the algorithm goes. So for fixed dimension vector Q, so this is equivalent more or less to give a delta vector or weight vector. For the quiver, well, without loops or without potential, that's the same thing. Then we consider the set of all real vector within this bound. So I mean, given this Newton polytope, the normal vectors are all bounded. I think it is difficult to give a sharp bound, but it's quite easy to estimate some rough bound. So then consider all the real delta vector within this bound. So by real vector, I mean those delta vector correspond to the clusters. Then I can use the mutation algorithm to compute the the tropical F-polynomial of those vectors, those real delta vectors. So this tropical F-polynomial, the calculation, I think, is just a tropicalization of the usual mutation algorithm. The mutation algorithm to compute the F-polynomial is quite expensive, but to compute the tropical version is quite cheap. Then the exchange graph of the acyclic quiver is connected. So that simply says for each delta, we can always, by applying certain sequence of mutations to get this delta. So this kind of tropical F-polynomial can be computed in finite step. And finally, somehow we can compute the home in one direction, but then the other direction is determined. Then I'm able to determine the Newton polytope. So it's not a great algorithm, but it works. Just okay. I think I'm done here.